All right, so we skirted over some maths. Right? We're only going to look at it very briefly. But AES GCM uses GF2 to the 128, which is a big version of the 2 to the 8 that AES uses. Now, we did talk about the AES maths briefly, I believe, in a previous video, but it was many years ago and I can't remember that far back. But I just wanted to show you a little bit of an intuition about what's happening and why, for example, repeating this nonce a second time causes you such a headache, right, using GCM. Because actually one of the big...
It's a bit like stream cipher, like in Enigma, and
It's a bit, yeah. The thing about a normal stream cipher is if you reuse the nonce, you can start to recover the message. But in GCM, you also can start to recover H and then forge new messages, which is almost worse. And you can also recover the message as it happens. So GCM has this particular weakness because of the way that it's constructed that means that it's very, very vulnerable to nonce reuse. Now, that isn't necessarily a problem because as long as you're absolutely clear about using a counter here, for example, and never repeating it, then that's probably okay. But you just have to bear in mind that if you're implementing this and you ever reuse this a second time, you have a serious, serious problem. So that's worth knowing about. Okay, sort of the brief primer on finite fields is, what we're doing is we're representing our binary data as a polynomial. So for example, in an 8-bit, you would have maybe 1000 1001, right? That's an 8-bit number. So that has an integer value, right? It's a byte, but we're actually going to represent it as x to the 7 plus no x to the 6, x to the 5 or x to the 4, plus x to the 3, x squared x plus 1, right? And any binary value can be represented this way. And then when you multiply them together, instead of doing a regular integer multiplication, which will overflow possibly, we're going to do a multiplication of these polynomials and then reduce them modulo some special modulus polynomial.
Right, I'm feeling a bit rusty on polynomials, so let's rewind a little bit. And how did you get the x7 from where the ones are? Is it from where the ones are?
So this is the 7th bit, this is the 0th bit, we're going 0 indexing. So this is x to the 0, x to the 1, x to the square, x squared, x cubed, x to the 4, x to the 5, x to the 6, x to the 7, right? And because some of these are 0, we don't have any of those things. And so we only have x to the 7 plus x to the 3 plus 1. Another example would be 00000011, which is x plus 1, because you don't have any x squared or x cubed or anything like that. Now you could multiply these two numbers together, and what you would have to do is multiply x to the 7 plus x cubed plus 1 by x plus 1. And that happens much like a normal polynomial multiplication. So this would be x to the 8 plus, so x to the 8 plus x to the 7 plus x to the 4 plus x to the 3 and so on. And you'd multiply this out. But then your number is overflowing over your 8-bit value because you have an x to the 8, which would be another one here. So you have to reduce it. Now in AES, you reduce it modulo this Rindal polynomial, which is x to the 8 plus x to the 4 plus x to the 3 plus x squared plus 1, or something along those lines. I might have misremembered it. But the point, I guess, is whatever your data is, you multiply them together. If you overflow, you're going to need to reduce modulo this polynomial, and that polynomial is just part of the spec. So in GCM, that polynomial is x to the 128 plus x to the 7 plus x squared plus x plus 1. So what does that mean? Well, you would divide by this, and you find out what the remainder is. Okay. Now, I won't actually work through an example like this. It would take quite a long time for an x to the 128 with lots of different coefficients, but that's the idea. But the take-home message is that you have two 128-bit strings, you represent them as polynomials, and you multiply them together, you reduce, and then you have another final output 128-bit string. So whatever you do when you multiply things together, you're going to end up with another 128-bit value. It's never going to overflow. Okay. So now if we look at what our encryption scheme is doing, we're actually calculating a function based on H and these inputs. So you might have something like AAD multiplied by H to the 1, 2, 3, 4, H to the 4. I might have got my degree slightly wrong, but you get the idea. Plus, because XOR is plus, right? C1 times H to the 3 plus C2 times H squared plus C3 times H to the 1, right? I have got them 1 by 1 because that's 1 as well, right? So that plus length times h, right? So that will be h to the 1, h to the 1, h squared, cubed to the 4 to the 5, right? You get the idea. So actually, this is itself a big long equation. Now the problem with an equation like this is you can actually solve these equations to find out what h is if you know all these unknowns, which is why we add this in. So now we have plus this value here, which let's just call it the encryption of n, right? Like this. That is essentially a random looking variable that we don't know. So we know a lot of these things. We know AAD, we know C1, we know C2, we know C3, and these equal the tag. Right? Let's suppose this wasn't there, you would have all the information you needed to reconstruct H and start forging messages, because you would basically find out what a root or a solution to this equation was, and then you could say, oh, it's H, right? And now I've got H, I can start going, fiddling about with this, changing this, fiddling about with this, and recomputing a nice valid tag, which will cause you a huge headache. But that's there, right? And so that's a problem, and that's why we have this link here. But if you reuse your nonce a second time, and you XOR these two things together, this is going to be the same both times, and it's going to undo itself. So essentially, you're going to have two messages, another AAD, another C1, another C2, C3, and L, and the same EN again, which is going to go away, and then you have that big problem. Then you can calculate possibilities for H, work out which one the correct one is, and then you can start to forge messages. Right? So this is a very nice scheme. It's very, very quick. Right? And so you can calculate a lot of this in parallel. You've just got to work out how many copies of H you need, and then you can multiply this, on one core of your PC and this on another core. I'm oversimplifying, but you get the idea. But it does have that vulnerability that if you use the nonce a second time, you have this set of equations which are going to help you reconstruct what H is, and H is meant to be a secret. Right? So the question, I suppose, is why don't you just encrypt this? Right? You could encrypt the tag using EK, and that would be a solution, right? You wouldn't be able to then do this. And the answer is it will slow down your code slightly, right? Because you're trying to do this in parallel. Maybe you're doing this bit plus this bit plus this bit, right? They all finish at exactly the same time, and now you've got to wait for AES to come along and encrypt the whole thing. That's slow. And we're talking about every single message sent on the internet. Maybe you want it to be as fast as possible, right? So it's a security trade-off, I guess. And it's only a security trade-off, I guess, if you reuse this nonce. If you don't, maybe it's fine, right?